Hi, everyone. I hope you're doing well today. We are going to talk more about our power transformations. And so previously we talked about, you know, um, what if I'm told there's a cubic relationship between two variables or whatever. So you're going to be like told a specific relationship. Um, and we did some practice on that. But what if I'm not told that? What if I don't know if there's a power relationship or what relationship there is? What should I do? So that's what we're going to talk about today. But before we really jump into transformation specifically, I wanted to do a quick review of um, rules of exponents and rules of logarithms. And now, before we really go through this, I don't want you to panic. You're not really going to be using too many of these rules in, your everyday problems or on assessments or anything like that. But I want you to really understand where this is coming from. And so as I'm going through like the lesson today, I don't want you to be thinking like, wait a minute, what's that? How did she get that? So just quickly, if I'm simplifying expressions with exponents, this is what we call the first rule here is our like power to power rule. Um, when you raise a power to power, you multiply the exponents. The second rule is called the multiplication rule. When you multiply, you add the exponents. And the third rule is called the division rule. When you divide exponents, you subtract. Okay, so now that we have reviewed some of our rules of exponents, let's talk about our rules of logarithms. So up at the top, logarithms are really just another way to rewrite exponents, exponential equations, right? And so we have our three rules of logarithms here. I think they're called the multiplication rule, the division rule, and the power rule. We know like a common logarithm is when we have log base 10. So if we just have like log of x, that really implies that the base is 10. Natural logarithm, when the base is e, we call that ln or natural logarithm. All right. So hopefully these rules should look familiar. Again, not to intimidate you and this isn't like an algebra 2 class, but it's just to kind of help you better understand what we're doing today. All right, so again, like I said in the beginning, the objective today is, you have a set of data and you're not told what type of a power model or whatever that it is that you need to use. So how do you figure it out? Well, a scatter plot, if you have a power relationship, a scatter plot of the logarithms of both x and y should produce a linear pattern. And we're going to talk about why. So if you have a power model, your equation is going to look like this. Y is equal to a times x to the p. So, y is your response variable, x is your explanatory variable. And then a and p are constants, just plain old numbers. So p is your power. So if I do some math, and this is why I reviewed these rules with you, but if I do some math to this equation and take the logarithm of both sides of the equation, this is what I get. So the log of y is equal to the log of a times x to the p. Now, I'm going to break apart that right side or expand it using my rules of logarithms, right? So if I have like a times x to the p, I can break that into the sum of the log of a plus the log of x to the p. And then if I have a power, I can use my power rule to bring that p kind of like out in front. So now I have that log of x to the p became p times log of x. hopefully this should kind of look familiar. Again, you're not going to have to do this on an assessment. I'm just showing you this so that you kind of understand where this is all coming from. So if I look, this is completely, expanded here. This is going to show us a linear relationship. Log y, log x, and don't forget that a and p were constants, just numbers. So if I take the log of a, the log of a number is just going to give me a number. And then p was a number as well, right? So my linear relationship is here. It's like log of y is equal to a constant, or in other words, my y-intercept, plus p, or in other words, my slope, times the log of x. So there's my linear relationship. Now, I took log base 10 here of both sides. I could have taken log base 7 of both sides. It doesn't matter. Or I could use natural logarithms. The math, kind of the algebra still works the same. So it doesn't matter if you take the log of x and y, or the natural log of x and y, or really the log base whatever. Typically in statistics, we use like log base 10 or natural logs. All right, so let's go back to this example problem that we've been looking at. So as a quick reminder, we have a certain type of Atlantic Ocean rockfish, and we want to predict the weight of the fish from its length. And we said, in previous classes that we can reason that, weight is kind of like volume. So it's like, a cubic kind of relationship with the length. Here's the raw data. So now if we're gonna, instead of like just cubing the length or taking the cube root of the weight, let's test out this new idea. What if I just take the log of both the length and the weight? And so in previous classes, I told you I a lot of times write down like where I have my different values stored in my calculator. So in this case, I've already typed in the lengths into L1 in my calculator and the weights into L2. And this is my X and this is my Y, right? And so now I'm going to use my calculator in L3. I'm going to take the log of L1, or in other words, the log of all the lengths. And then in L4, I'm going to take the log of all the weights, or in other words, the log of everything in L2. All right, so let's pull out our calculator. And let's do this math. So if I go to stat edit, here's L1 and L2. Here's the lengths and then the weights, right? So I'm going to scroll over to L3, go up and highlight L3, and I'm going to take the log of every, oops, sorry, it already gave me parentheses, of everything in L1, so second L1. When I hit enter, so this is now the log of 5.2, the log of 8.5, etc. And then in L4, now I want to take the log, so I'm going to scroll over to L4. Notice I highlighted where it said L4, like the header there. And I want to take the log of everything in L2. So this is the log of all the weights. So if you want to, you could fill in all these values here in the table on your paper. But then I'm going to make a scatter plot. So I'm going to make a scatter plot of what does this look like? What does the log of the lengths plotted up against the log of the weights look like? So I'm going to go into second stat plot. I'm going to make a scatter plot, but now I want like L3 versus L4, right? I'm going to hit zoom 9 or zoom stat. Wow, look at that. So I have this really linear relationship. Look at that. it went from that curved pattern to this linear pattern. So if you want to take a second, you can draw a rough sketch of that on your paper. And next thing, I want to perform a least squares regression on the transformed data points. So the log of length versus the log of weight. So I'm going to go back into my calculator, second quit to take me out to the home screen, and I want to go stat calc option 8. I want to do a linear regression of the log of the weights versus the log of the length. So L3, L4, and then if I wanted to, I could store the regression equation into y1 or y2 or whatever function I would like to. And this is going to be when we store something in here, you'll see why in a couple minutes. It's not quite as useful as it was previously. I'll explain that in a little bit, but you can still do it if you want to. Hit calculate, and then here's my linear regression. So I'll leave this up on the screen for a second. Make sure that when you do your linear regression on your calculator, you get the same thing. And then let's write this down. All right, so back over here. So perform the least squares regression, and let's write down this equation. So my least squares regression equation was y hat is equal to negative 1.899 plus 3.049x. But don't forget, really, we use, this is not just like a regular x and y, we used x being the log of length and y being the log of weight, right? So if I want to think of my equation in terms of the original data, so if I want this equation in terms of like length and weight, so x equals length, y equals weight, I can just take this x instead of a regular old x. This would be the log of x. And my y hat now becomes the log of y hat, right? So here's my regression equation. And then it asks you to find and interpret the r value and the r squared value. So again, remember, this is everything that we've been doing. We're just now interpreting it in terms of, instead of x and y, we're talking about like the log of x, the log of y. So my r is 0.999. So this tells me that there is a strong positive linear relationship between the log of the length of the fish and the log of the weight of the fish. And I might even want to add that there's like a very strong positive linear relationship, because that r value is really close to 1. And the r squared was also 0.999. Again, really high, really close to 1, right? So again, r squared tells us about the variability in the y. So in this case, the y is not really y, it's the log of the weight, right? So this is going to say approximately 99.9% of the variability in the log of the weight of the fish is due to the linear relationship between the log of the length and the log of the weight of fish. Sorry, trying to squeeze that in there. All right, so there are my interpretations. Now we should look at a residual plot. So I'm going to go back into my calculator. And remember, I already did this, I performed this linear regression, right? So the residuals have been overridden and they're now stored in the calculator. So to come up with my residual plot, I go back into StatPlot, and a residual plot is always the x values versus the residuals. Well, our x values that we used were in L3. It wasn't really x, it was log of x, right? And now in the y, I want to go second list, resid, and now I'm going to zoom 9. So there's my residual plot. It looks pretty randomly scattered. I definitely have a higher concentration of x values over here on the right-hand side. But if you remember when we looked at the original, let me go back a quick second. When I looked at the original data, so log versus log, I saw the same thing. There was this higher concentration of x values over here, right? And that's okay. So I'm going to see that come up on the residual plot as well. Let me get the residual plot back up. So okay, so there's my residual plot. So it looks like that the y values are pretty randomly scattered. So what does that tell me? That tells me it's a good indication that the linear model is appropriate, that the actual scatter plot of log of length versus log of weight was approximately linear, right? If you wanted to, you could make a rough sketch. So question number 15, it says, does this model appear to be a good fit? How confident are you in determining the winner of the tournament using this model, and why? So I would say yes. The answer is a definite yes. It appears to be a good fit. And there's a bunch of reasons. If you're asked a question like this, please do not just tell me, yes, R is close to 1. That's not enough. You have so much information here. You need to give me as much reasoning as you can. So the first reason is that the scatter plot of log of length versus log of weight was linear. The second reason was that the residual plot was randomly scattered around the line y equals 0. We also have an R and R squared that are really close to 1. So for all of those reasons, this is, we think that this model is a good fit. And the other thing that I forgot I wanted to show you as well, if I look at this residual plot and hit trace, look at the size of the residuals, the y values. They're all pretty small. They're very close to 0. So that's another good indication that the linear model is a good fit. My residuals are all very small, right? Okay, so next part. Suppose Dan caught a fish that's 36 centimeters long. According to your model, how much does the fish weigh? So this should look kind of familiar. We made this same prediction based upon the other two models that we came up with previously. So we need to plug in 36 for x, but don't forget, our equation is really log of y hat equals negative 1.899 plus 3.049 log of 36. So you're plugging in 36, and you're going to simplify that right side of the equation. When I simplify the right side of that equation, I get 2.846. But remember, that's not my answer. It's really the log of y hat equals that. So how do I get what is y hat really equal to? So this is a logarithmic equation converted to an exponential equation. So 10 to the 2.846 is equal to y hat. So this part, remember I told you before, you don't have to know too many of these rules of logarithms and rules of exponents that we kind of went through earlier. This is one that you are going to need to do. You are going to be able to solve an equation like this for y. So if I raise 10 to the 2.846, my y hat value equals 701.724, and these are measured in grams. So how confident are we in this prediction? Well, if I go back and look at the original data, the length here is 36 centimeters. That's within, the domain of the x values that they gave me in the original data. The relationship we said is a really strong relationship, so I'm pretty confident in this answer. And if I go back really quickly, jump down here, if I compare this answer to flip to previous problems in your packet, like number 10, our answer to number 10 was 688.855. So it's a little bit off, but it's pretty close. And then we looked at a model in class, it's not in this packet, but where instead of cubing the lengths, we cube rooted the weights. And that response, or that output, was pretty close as well. And then you can make your prediction in number 17. So log of y hat is equal to negative 1.899 plus 3.049 log of 44. And now before I even do anything, 44 is an extrapolation. So I don't know if this pattern is going to continue or not. So when they ask me the question about how confident am I, I'm not quite as confident. But I'm still going to go through the process of plugging in and making the prediction because it asked me to. So log of y hat equals, when I simplify that right side, I get 3.112. That's a logarithmic equation. Convert it to an exponential equation by taking 10 to the 3.112 is equal to y hat. And then so my y hat is 1293.859 grams. Keeping in mind, if from the very beginning, I asked you to take the log of the lengths and the log of the weights. But I could have said, take the natural log. If I had taken the natural log of everything, my equation would have looked a little bit different. So this whole equation would have been different. The slope and the y-intercept would have been different values. But then ultimately at the end here, these would have been like natural logs, you know what I mean? Natural log. And then when I convert, I would have taken like e to the whatever number. My ultimate answer, my prediction should be still the same. Or I should say, not exactly the same, might be off a little bit because of rounding, but it should be very close. All right, so we went through the prediction now with, having a whole list of data, having like the raw data where you actually did the transformation. You took the log of both sides, the log of x and log of y, I should say. You're not always going to have to do that. Sometimes they're going to give you the computer output. So we're going to look through the same exact problem. What would this look like if I was given the computer output? All right. So let's look. This is the same exact data. Our answers should all line up and still be the same. So we took the log base 10 of the values for both variables. Here's some computer output. So notice here's my scatter plot. It's the log of the length versus the log of the weights. This is what we saw in the calculator, right? The residual plot, how did I know it's the residual plot? Because it says log of the length, which is x, versus residual, right? And the residual plot looks randomly scattered. So down at the bottom, this is the output that came out from the computer that gives me the slope and y-intercept, r-squared, all that stuff. All right, so based on the output, explain why it would be reasonable to use a power model to describe the relationship between weight and length. Again, why is it reasonable? It's reasonable because I have this linear relationship here when I graph log of length versus log of weight. The residual plot is randomly scattered. The R squared is really close to 1. The standard deviation of the residuals is pretty small, which means the average residual is, close to 0. So you would mention as much of that as you could, okay? Part B, give the equation of the least squares regression line. Be sure to define any variables you use. So remember, the least squares regression line constant is always going to be your y-intercept, and then the x variable is going to be listed along with the slope. Remember, for right now, we're ignoring all this stuff. You never are going to use in this class the r squared adjusted. Here's your r squared, which we'll come back to, standard deviation of your residuals, right? But so your equation is this. Now, we defined our variables. In this case, we didn't use variables, but you could have written log of y hat, log of x. But off to the side, you got to make sure you're right, like x equals length, y is equal to weight, right? We have to be mindful of defining our variables. So there's our equation. Same exact equation we got when we used our calculators, right? And now part C, suppose a contestant in a fishing tournament catches an Atlantic Ocean rockfish that's 36 centimeters long. Same exact question we just did in the packet, right? Use the model to predict the fish's weight. So we're going to plug in 36 for x. And then we're going to simplify that right-hand side, right? Convert this logarithmic equation into an exponential equation. And then raise 10 to the 2.84, and you get 702.1 grams. All right, so that's it. I would strongly suggest that you do some practice from the book. I've left some additional practice for you to work on. And please email me if you have any questions. Thank you so much for watching. Have a great day.